And I think if you are interested in this area, it's still potentially possible for him to be a co-supervisor. So he will have to find a supervisor in the computer science department and then co-supervise if you're interested in this area of research. So for today, let's give the floor to Joseph.
Okay. All right, so hi everyone. So as Professor mentioned, I'm Joseph J. Williams, and so I'm in information systems analytics. But as I think you'll see, a lot of my research is human-computer interaction, machine learning, artificial intelligence. So I'm always interested in collaboration. So if you are doing a project that's AI or machine learning related, and you think it would be nice to see how it applies to a real-world setting, like you want to test your algorithms out to build better online courses, or to even apply an algorithm to make, ideally more intelligent. That's something I'm always interested in talking about. So you can always feel free to email me. Oops. Yeah. So you can feel free to email me. I'm at williams@com.nus and just say hello or ask me for more information like the slides. Harold, so Yarazek, who have a lot of overlapping interests. Also David Su and Wieston do reinforcement learning work. So I'm also happy to chat about that. Even if you're interested in doing like a small side project, I think this is often the best way to kind of see if there's a good overlap in interest. So, you think maybe it's in MapBook actually? Huh? I wonder if it's in MapBook coordination. Okay, great. Okay, so I'll just kind of dive into it. So the kind of key idea here behind a lot of my work is basically we're interacting with technology all the time. For example, you look at websites, you use apps on your phone, you do use ideally for learning. How do we actually take any piece of technology and make it more intelligent? Actually make it like a system that's going to test out new versions of itself and figure out what's going to help different people learn or help different people change their behavior. And so that's what the talk is about. So one thing I'll mention, since it's blocked here, is, does anyone here know where I'm from, like where this kind of unusual accent is? Yeah, so I'm from Trinidad and Tobago. So like Singapore, this is an island, but it's actually in the Caribbean. And I have to tell people this before every talk, because otherwise they say they miss my talk trying to guess where I'm from. So I know I'm from Trinidad and Tobago and the mystery is solved, so I guess I have your full attention. So what I'm really excited about is the promise of software to enhance learning. If you look at MOOCs, or massive open online courses, anyone can now go and start watching videos, they can solve problems and get feedback. It's also permeating on-campus courses. So many undergrad students do a lot of learning from problems in Ideally. I also see learning as actually ubiquitous. It's much broader than just formal education. If you think of mental and physical health, issues like depression or addictions like smoking, what's one of the best ways to get people to stop smoking? Actually, it's teaching them something called cognitive behavior therapy. So I've done research on how you actually help people learn cognitive behavior therapy, which is techniques for reflecting on your emotions in a way that actually helps you to change your health behavior. So by actually just learning how to reflect in the right way, you can actually eat more healthy or do more exercise. In the United Kingdom, doctors can actually write a prescription for cognitive behavior therapy. So I really see learning as in everything. Learning formally, like when you're in school, but also learning in everyday life. Learning how to change your behavior, how to be more healthy, learning how to make better decisions. But there's a problem. Anytime you're trying to learn from a resource, it always needs to be improved. And I think the problem is that no matter how well a teacher or a designer of an app creates something, you never know what's going to work until it's in the real world. So what I think we really need is that we have to have systems that perpetually improve, just like a real teacher does. If you think of an online problem, where someone might solve a problem and get the answer, then give an explanation for why the answer is right. A real teacher wouldn't say the exact same explanation over and over 100 times. They would actually naturally vary. They might explain things differently every time they speak to someone. And that would allow them to discover over time which explanations work best. It would also help them figure out how to personalize, which explanations will work well for different people. So my goal is that online resources, whether it's your personal website, an online course, or an app, shouldn't be static. They should actually be more like a self-improving system. So we need to actually be able to deploy resources into the real world in a way that they can perpetually improve, just like real humans do. To make that concrete, here's an example. Teaching statistics, an instructor might want to give students problems, but have these problems improve over time because otherwise students don't really learn. They don't get the key idea. Or in the context of something like health, a clinical psychologist might give someone a scenario to help them reflect on emotions. But this scenario is never really good enough the first time. How do we keep improving it? And so my approach to making any online resource an intelligent system is to use randomized experiments. So you've all heard of A/B testing. People in Facebook and Google are always testing out different versions of apps to see which ones get you to click or buy. But actually, experiments have a much longer tradition in science, in psychology, and education. There are many obstacles to doing experiments well. And so what I try to do is think of how do we design good experiments using behavioral science, and then use our machine learning to choose the best conditions for people. So my approach then is to reimagine experiments. Let's make them more collaborative, dynamic, and personalized. So my approach to HCI is that whenever we design an experiment, it could be on your homepage, it could be on explanations in a math problem, it could be on motivational emails to get you to go exercise. We choose the conditions, we decide what we're going to experiment on by drawing on cognitive science, which is what I did my PhD in. I did my postdoc at Stanford in instructional design. But we can run experiments that don't actually help people directly. And so I think the key idea here is that we have to build experiments where you can dynamically analyze data every time someone touches it, so you can improve it for the next student. So for example, if 10 students came in, instead of assigning people just 50%, 50% to message 1 or message 2, you'd actually get some data that would help you see, well, actually message 1 looks like it's more effective. And so after a period of time, you might update from 50-50 to 60-40 or 80-20. And so we can do this dynamic analysis. Then any experiment isn't just a scientific tool, it's actually an improving system. And eventually, this could lead to enhancement, where maybe everyone gets the best message, or it could even better lead to personalization. We figure out that different messages work for different people. So in my PhD, I applied Bayesian statistics and machine learning to modeling cognition. But now I actually use it to build self-improving systems that can apply algorithms in real time. So you can start experimenting and then result in enhancement or personalization. But what's missing from this? If we start with a fixed set of conditions, like A, B, or C, we don't really have a perpetually improving system. So I also build software that lets you keep adding new conditions. So every time you get a new idea or you get new data, you can actually add new actions. And so that this, in a way, never stops experimenting. It's almost like if your website was always improving because you could keep adding in new versions and test them out. Now, to do this, what I do is I draw on crowdsourcing and human computation from the field of HCI. So how many people have heard the term human computation before? So the key idea of human computation is that we often want to solve problems. For example, we build algorithms to try and figure out how do we give people personalized education. But often, human beings are some of the best computers around. So if we have an algorithm that's trying to figure out how we recommend lessons to people, how can we actually bring humans into the loop so that people are actually part of the algorithm? They're giving feedback or they're actually suggesting actions. So the idea behind human computation is, let's use technology to bring together people and algorithms in ways that can better solve problems, where we use humans to compute the things that algorithms can't yet. Now, this vision is really not possible with normal A/B testing. If you go to most education websites, if you look at most apps on your phone, you can't just do A/B tests that are dynamically improving. And so a big part of what I've done has been a bit of software engineering. So I developed this AdaptComp or MOOC-led framework, which basically means that if you implement an experiment this way, it guarantees that you can plug in these machine learning algorithms and you can dynamically improve and personalize over time. So we have an overview. I started with this vision. How do we take any software and make it a perpetually improving system so it helps users? The approach I outlined is to reimagine experiments to be collaborative, dynamic, and personalized. I'm going to skip over in 1 minute just examples of experiments I've run, because what I really want to get to is examples of systems I built and the algorithms I've used to do this dynamic improvement. I'll also talk about the first directions towards discovering how to personalize, and then close on future work, where I'm especially interested, and I think some of you may be, in terms of what are the next steps? How do we actually do research that's going to bring together designers of software with machine learning researchers so that we can actually constantly improve? And how do we think about applying this kind of work to education as well as to settings like health and business applications? So you don't have to catch this. I'm going to quickly show examples, experiments I've run. So I've run experiments on math problems, for example, adding motivation messages in Khan Academy, or adding actually questions, prompts to reflect. You can see that almost any software you interact with, by adding in messages that motivate you or questions that help you reflect, you can actually change what users are doing. So this was a study that I ran on Khan Academy. So that's one of the large online websites in the US with millions of users every month. And what we did was actually experiment with different motivation messages based on psychological theory. And what we found is that even when teachers thought there'd be no difference, if you use psychological theory, you could actually have a big effect on people's motivation. And this actually led Khan Academy to launch a campaign where they, after the experiment was run, they then sent messages to millions of learners, trying to get them to believe that they could learn anything. Another kind of experiment has been questions, prompts to help people reflect. So in this line of work, after someone solves a problem, I would actually prompt them, well, explain why you think the answer is correct. So the idea here is that we can compare different prompts. For example, explaining why the answer is correct against writing any thoughts you have about the answer. And the key takeaway, again, is that even if you think these prompts are very similar, they have very different effects on learning. Explain why, like why they did something, why a fact is true. This really helps them generate knowledge. And you can think of this as a form of human computation. How do we actually ask learners just the right questions so that they can construct knowledge, so they can actually optimize their own learning? It's like helping them help themselves. So these are just two example experiments on motivation messages and questions to reflect. I don't actually get at what I'm really interested in for the future, which is how do we do experiments where you keep adding new conditions and where you use dynamic analysis to choose what's best? That's going to be in the context of figuring out which explanations do we give people for how to solve problems. How well are people in the back hearing me? Put your right hand up if you're hearing me well. In the back row, are you hearing me? Okay, left hand if you're not really hearing me. Maybe I should I'll speak a bit slower because I know it's harder to process an accent. It probably sounds like I'm talking twice as fast as other people. Okay. So I'm going to present this adaptive explanation improvement system, or AXIS. So the key idea here is that we want to figure out which explanations are actually going to help students.
The system, or is it because of the sharp?
I think it's the system.
It's a connector.
You think so? So what do you think I should try? Should I try and unplug it or plug it back in? Or?
But is it? It's not because the system go to sleep.
No, it's not that. No.
Maybe make a complaint.
Is that adapter part of it?
No, this is my own adapter I brought. Yeah. Okay. Let me unplug and plug back in quickly. And wave, do some magic.
Give it a few kicks.
Yeah, I just got this last week. It's a new MacBook, and USB-C is amazing, except it will be amazing, but nothing in the world uses it right now. So I had to buy like 10 adapters. Okay, so kind of thinking about this. So basically, it's kind of a humble example, but let's make this explanation like an intelligent agent. We want this problem to be able to generate explanations on its own and discover which ones actually help people. So it's not a super intelligent agent, but it is an intelligent one. And so what's our approach to that? It's actually through human computation. So what we do is we ask learners to explain why they think an answer is correct, because it helps them. Then we can actually take the explanation and provide it to future people. So we have a way of continually adding new actions. So this problem is getting smarter because it can keep getting new ways to test out explanations. But these explanations may not be very good. So this is why we actually want to use machine learning to dynamically analyze which explanations learners find helpful, and then use that data to change what future people receive. So here's the interface learners interacted with. They would see a problem, they'd attempt it, and eventually get told the correct answer. Then they'd be given an explanation, which comes from the current set of actions in the system. We'd ask them to rate how helpful was the explanation for your learning on a scale from 0, not at all, to 10, extremely helpful. So then we get some signal about what's useful. And then we ask them, well, to help you learn, why don't you explain in your own words why the answer is correct? So learners are doing it selfishly, but you can imagine what we're going to do with this. If the explanation they give is above 50 characters and they indicate it might be helpful, we actually add it to our pool of explanations, so the system can keep increasing. So now the question we have is, how would we formulate this problem of dynamic experimentation? So have you all heard about the exploration versus exploitation trade-off? The kind of key idea behind that is that you might have a set of actions you want to take. For example, explanations to present to people. And you want to explore to see which ones do learners actually rate as helpful. On the other hand, you don't just want to explore, because every time you give a learner a bad explanation, it's hurting them. So you want to quickly use that data to put it into practice. And so in general, reinforcement learning kind of tackles this problem. How do you take actions and explore which ones are useful, but then quickly exploit that knowledge, put into practice? Bayesian optimization, which Brian Lowe can say a lot more about, is another approach to this, where you're basically thinking, which actions am I trying to take, and how do I quickly figure out what's working well? So I'm actually formulating this as a multi-armed bandit problem, which is actually a very special, simple case of reinforcement learning. You might have heard of MDPs or Markov decision processes. Actually, a very simple case where we assume that every action we don't look at the repeated effects. Someone comes in, we take an action, and we just want to take actions to optimize reward. Then someone else comes in, it's like a new person. So the key idea behind a multi-armed bandit formulation is that you have a set of actions, in this case, a set of explanations. Actions to maximize reward. In this case, you're trying to give learners the highest rated explanations. So you have to test them out, but you want to discover as quickly as possible which ones are highly rated. You also need a policy. For learner 1, 2, 20, which explanation or action should you take? And the approach we take here is to use an algorithm for multi-armed bandits that does what's called randomized probability matching. And this algorithm is called Thompson sampling. The key idea here is that you can understand the policy as basically being weighted randomization. So you could think, if I have no idea which explanation is better, then maybe I give them 50-50. But if I get evidence, then I might try and compute, well, if 5 people rated it a 6 for explanation 1, and 7 people rated explanation 2 a 7, what's the probability that explanation 2 is actually the highest rated explanation? So in this example, you might imagine, well, 15% chance explanation 1 is the highest rated, 65-20. So you actually compute those probabilities based on your model, and you use that as your policy. So the probability of assigning people to a condition is actually the probability that that's the best condition. So this, of course, requires having a model, a set of parameters you want to estimate of these explanations and actions. In this case, we just to quickly state, we actually assume that the probability of an explanation being rated helpful follows a beta distribution with parameters alpha and beta, and that the rating follows a binomial distribution where there are 10 samples, and the probability of success is the probability of an explanation being rated as helpful. So just intuitively, you can think that if you give someone an explanation they rate as an 8, that's as if they gave 8 thumbs up and 2 thumbs down. So you're kind of constantly getting data about how highly rated these explanations are. And so I'll say a bit more about this, but the basic idea here is that we use Bayesian inference, so that at every point in time, whenever someone gives a rating of an explanation, you can update your estimate of what the mean rating is for that explanation and how confident you are in that rating. And then you use that to calculate, well, what's the probability of this explanation being the highest rated? So I'm actually going to give you a little bit of background for those of you who may not be that familiar with this topic. So to say a bit more about multi-arm bandits, like I said, there's a set of actions, in this is explanations. You want to take them to maximize reward. There's also a set of ideas that I'll discuss later, which are called contextual bandits. What if actually there's not a single explanation that's best for everyone? In this case, then you're incorporating context. So you want to say, well, what are the features of students? How much knowledge they have, what their verbal abilities are like, what they've done right or wrong. Which actions will give them the optimal outcome given that context? And this actually ties into things like markup decision processes, where you can see in the MVP, you actually think about there's a state of the world. For example, the state of the world could be features of a user. And then you take actions which are not just trying to maximize reward, what's the outcome, but also change the state of that user. So multi-arm bandits are a simpler case of this, which have actually been found to work really well in applications. Some standard algorithms for these are things like epsilon greedy, where you basically could choose the explanation that has the highest rating so far, except it could be that it only looks the highest because you got to buy a sample of data. So epsilon greedy means that epsilon percent of the time, 10%, 15%, you just choose another action at random. The methods like upper confidence bound, where you estimate the mean rating, and then you actually add bounds to that reflect how confident you are that it couldn't actually be higher. And that's actually a deterministic algorithm used to choose it. And so Thompson sampling kind of fits in here as being a Bayesian algorithm that lets you incorporate prior knowledge, but also one that's probabilistic and I think more interpretable for these kinds of applications to users. So just to remind you, the key idea here is that in Thompson sampling, the probability of choosing an action is the probability that it's the best action based on the data you have so far, interpreted via your model. And to say just a bit more about beta distributions, well, maybe actually, how many people are like totally familiar with beta distributions? So if you implemented them, you understand them well. Put up your hand. How many people could benefit from just hearing a little bit more about them? Okay, so a beta distribution is a really nice intuitive statistical distribution for probabilities. So let's say actually, you tell me, Joseph, I'm about to give some explanations to people, and I'm wondering, what's the probability that explanation 1 is the best one to give? Well, you actually might say, well, I don't know, is it 40%? Is it 60%? But instead of just giving a number, you may actually want to say, well, I don't know what the probability is, so I actually want to put a distribution over what that probability could be. So these are all beta distributions. So instead of saying, Joseph, the probability that explanation being the best, the probability of that explanation being the best is 50%. Instead of saying that, you say, actually, there's an X% probability is 0.2. There's a higher probability is 0.3, and so on. So you're actually using this to put a distribution over what that probability could be. And of course, now, at the beginning, you might think, well, I think it's most likely 0.5, but it could also be higher or lower. Sorry, what's the probability that an explanation is the best? Well, I think it's probably 0.5, but it could be a bit higher or a bit lower. How would you update this distribution? Well, actually, every time you see someone give a rating that's really high, so if you see someone give a rating that's a 9 out of 10, then you might actually shift this distribution. You say, actually, I think the probability that's the best explanation may be higher than I thought. And so basically, the parameters of the beta distribution influence to what extent it's shifted. To what extent you believe, oh yeah, this is definitely the most likely, the best explanation, or actually, I'm pretty sure this is not. And how does it shift? Well, you can basically think of these parameters as representing the number of successes you've seen so far and the number of failures. So in my example of an explanation, if someone rates an explanation as an 8 out of 10, well, you can think of that as basically saying, well, that's as if this person said, I want to give that 8 thumbs up and 2 thumbs down. So it's as if a rating of 8 out of 10 is like 8 successes and 2 failures. In distribution, you actually then can update these parameters using a feature of conjugate distributions, where actually you can actually just add the ratings into the parameters of the distribution. So it actually makes it very easy to update. So for example, so let's say actually you start off where you're saying, well, the probability of an explanation being the best or is following a beta. So let's pretend that we're going to start with beta of 19 and 1. So what does beta of 19 and 1 mean? Well, that's beta of 9 plus 10 and 1 plus 0. So it's as if before seeing any data, you think, well, I've seen one person give it a rating of 9 and one person give a rating of 10. So that's your prior. You're acting as if, well, I haven't seen data so far, so let's imagine that every explanation has gotten 1, 9 or 1, 10. Then actually, someone gives it a rating. So someone rates it an 8. But what you can then do is actually, instead of your beta distribution being beta with alpha beta or beta with 19 and 1, then you actually can just add the successes to this one and add the failures to that. So now you have a beta distribution where it's 19 plus 8, beta plus 2. So the kind of key idea is this is a really simple, intuitive way to say, here's my prior guess for what kinds of ratings people have given. Every time someone gives another rating, I want to kind of update my estimate. And here's actually a good way using conjugacy to quickly update the beta distribution where it has the same form as before. And these are very easy to work with and implement. Any questions on that? Or Brian, feel free to jump into some clarification. It won't be intuitive the first time you get it. And we're talking about probability distributions over probabilities, which is always kind of confusing. So I'm happy to explain more. Yeah?
Have you considered the noise in the way? Because some really can be counted out on it.
Yeah, so I think this is a great point. So you're talking about more sophisticated models, right? So right now we're just assuming every rating is just a good readout from what someone has said. Now, there's always some noise that's kind of inherent in this, right? Like, for example, let's say the probability of it being, let's say that parameter is 0.8, which should correspond to rating 8. There's always going to be some variation. So it's accounting in some way for that. But what you could also imagine incorporating would be other reasons to think there's extra noise that we're not accounting for. For example, if some people give really bad ratings and some people give good ones. So then you could actually think of using hierarchical Bayesian models, for example, to try and account for that. Or you can, this is really the simplest kind of implementation, and there are lots of really interesting directions. So especially people more on the machine learning side, I think you'd be especially interested in thinking about which models here would be most appropriate and what are the advantages. And I can think about, well, how does that correspond to actual applications? So this seems to work okay in what we've used so far, but there may be settings where exactly what you said is true. We actually think that some students are going to be very noisy in their ratings, and some are going to be correct, more precise. So we might actually want to model that. So if we have a more sophisticated model, then we can actually do much better in our estimates. Okay. And so just to kind of, I'm repeating things a lot just so you kind of get it, but you could think of the prior ratings as being like 9 or 10, 9 or 10. One rating of an explanation is being 9 or 10. 1 and 9, 1, then 1, 10. And then actually, here's what people actually rated. Explanation 1 gets a 6, an 8, a 6, a 7. Explanation 2 gets a 3 and a 2. Explanation 3 gets a 9, 9, 8, 9, 10. And so you end up with some mean. You update the parameters to the beta distribution. And then you can use this to compute, well, what's the probability, given the data so far, that this is the highest rated explanation? Well, it might be 30%, or 15, or 55. So that's basically how this whole process is working. So in terms of actual deployment now, so we had this system, adaptive explanation improvement system, which we would give to learners, ask them to generate explanations, give them explanations, and get ratings. And so we actually want to kind of figure out which explanations are actually highly rated. So we deployed the system with 150 online crowd workers. So 150 is actually not that large a sample. That's on purpose, because I'm trying to build intelligent systems that can be used by anyone. It can be used by, the NUS course here on intro machine learning might have hundreds of people. If you want to use thousands, then it's actually in some ways easier to estimate these parameters, but I think it's a less challenging problem and it's less broadly applicable. It's nice to have methods that can actually work for these smaller samples because then any instructor can use them. So at the beginning, there's no explanations at all. Over time, there might be one, there might be a couple. And at this point then, as people are giving ratings and we're estimating the parameters, we're actually changing our policy. We're recomputing that the probability of explanations being highest rated is changing over time. And so this keeps happening, this updating over all 150 people. And at the end, you actually end up with the policy being a probability distribution over how likely different explanations are to be presented. And these probabilities should correspond to the probability of those of the highest rated explanations based on the data so far. So what does that distribution look like? Well, you could imagine that really it'd be nice to have something like this. This is definitely the best explanation. Actually, getting that kind of level of confidence would be extremely hard and require a lot more data. And I actually think one reason this system works well is because it doesn't try to do that. Instead, what you end up with is a probability distribution where there are a couple of explanations that are all reasonably equal, 18%, 30%, 18, 22. But then there's some that actually get very low probability. They're not likely to be highly rated, 4%, 3%, 5%. And so by having this kind of probabilistic approach, you can actually be much more efficient with the data. What the system was doing was actually selecting out higher rated versus low rated explanations. But do these explanations actually help people learn? So this is where the HCI and psychology part comes in. How do we actually test this idea? Explanations from Axis, and I ran a separate study. In this study, we gave some people just the original problems with no explanations. We gave them problems that actually had explanations that were sampled from Axis. We gave them explanations that were filtered out by Axis, so they got low probability. And as a gold standard, we compared these explanations that were written by the actual instructor. So to measure if this helps learning, what we did is before people saw each of these, we gave them a pretest. They solved problems in geometry and algebra. Then we gave them problems that either had explanations or didn't. Then we gave them a post-test. We gave them more problems that actually tested how they learned anything from going through this phase. So what you can see on the vertical axis is accuracy increase, whether they get any better at solving problems based on which condition they were in. So what's the kind of increase they get in accuracy in solving problems? So what's the key result? In fact, these Axis explanations result in significantly better learning. People are more able to solve problems than if you just give them the original problems. Even though they're coming from learners who are just writing things for their own reflection, by running it through this dynamic algorithm, we're able to actually select explanations that help learning. Well, what would a skeptic say here? They would say, well, of course, an explanation helps over none. You know, they actually have something to read. So as long as you give them any explanation, it's going to help learning. So that's why we included this filtered explanations. So these are explanations that Axis assign low probability, less than 5%. And what you see is that it's not just that any explanation helps. Getting these explanations that Axis give less than 5% probability is like getting no explanation at all. So the final question is, well, how good do Axis explanations have to be compared to those of a real instructor? Do they have to be 50% as good, 70%? What would make you think it was worthwhile to use the system? What's that? 100%. Wow, ambitious. Okay. Well, lucky for me today. In fact, Axis explanations were just as good as explanations from a real instructor. There wasn't a significant difference in how much they helped learning. Yeah. And so, in fact, the instructor reported the Axis explanations were comparable to their own. The kind of key takeaway from this work is, one is HCI. Here's a way of actually crowdsourcing from people, students who are explaining just because it helps them. But we can actually crowdsource new actions from them. And then we can actually use dynamic experimentation to see which explanations are highly rated and use that data to put it into practice to actually enhance the experience for future users. So this really is an intelligent problem. You start off with nothing at all. Over time, the system gathers explanations, tests out which ones are helpful, and keeps improving itself so that every new student gives data that will help improve the quality of the explanations for future students. Now, there's still limitations to this work and many interesting future directions. For example, could we actually incorporate teacher input, such as having teachers identify student explanations as being compelling or helpful to students? They think it's helpful, but actually it has a misconception. Or can we actually incorporate methods from natural language processing, such as figuring out which explanations are semantically coherent, or which of them actually correspond most closely? So this would be another way of actually adding to what we're optimizing for. Let's not just optimize for student ratings. Let's also optimize for other metrics. And again, the kind of formulation here is where you don't have to use NLP to logically say, okay, take this out, take that out. You actually incorporate all of these as constraints. You can take teacher judgments, you can take metrics of coherence from NLP, and you can take student ratings and combine all of these and optimize over time. One other set of work that I'm interested in is actually thinking about how this combines to recommender systems. So often recommender systems like Netflix, they crunch a huge set of data and kind of give you something. But how can we actually incorporate more dynamic experimentation into recommender systems? Where a recommender system might think, well, here are the options I think are good. Instead of just choosing the best, let's actually experiment with a certain subset so we can figure out how to tune them over time. And this year, I actually published a paper at ACM Rexis, which is about using recommender systems to recommend discussion questions in a MOOC to other people. This basic methodology can be applied much more broadly. So it's not just explanations and math problems. Imagine if people are watching a video and you ask them a question, like, what's the key assumption of naive Bayes? Well, when they write the answer, you could actually then use that to put on a discussion forum or a question answering system like Stack Overflow, where now you can think, I'm getting people to give answers to questions. And so now I actually want to use dynamic experimentation to figure out which answers are helpful, or which answers are helpful for different people. So I think you can all think of many other ways that you could apply these methods, different systems that you might be personally interested in. I mentioned this idea of human computation and machine learning and AI. So the kind of key idea behind human computation is humans, in your brain, you have a pretty good computer. In fact, it's better than all the others we have around. So how can we actually harness the crowd? The idea that you can make an API call out to get people at any moment in time on the internet. How can we actually use people as computational resources so they can help algorithms to solve problems? And so you can see that in the Axis system where we're using people to generate explanations, and we're also using people to give data and feedback about which ones are good. That's generating actions and reward signals. But there are many interesting future directions. For example, how can we actually encode expert prior knowledge? We assume that every explanation was just equally likely to be good. But you could imagine having teachers give ratings before we even start experimenting, and that could actually help guide so that we more quickly find out what's effective. This kind of gets into the whole issue of interpretable machine learning. When we're using these systems in someone's class, teachers want to actually understand, well, what is the algorithm doing at a given point in time? There's regret bounds that have been proved about an algorithm that will give something good. But that's not the same as actually being able to understand, well, for subject 29, here's the probability that they're going to get different explanations. And here's why. How can we actually give them interfaces that can help them understand how the average rating is influencing the probability that it's being presented? Or that they can understand, well, the more evidence we have, the more subjects and samples, the more likely it is to be presented. So this is kind of helping people in general understand when you've got algorithms for exploration and exploitation, how do they interpret the behavior at a given point in time? Understand how data is feeding in. Another key direction I'm interested in is interactive machine learning. So how can we actually bring people into the loop? Is it by having teachers give ratings or priors? Is it by actually having them look at explanations and modify them so they can actually improve the action space? Is it by actually having people decide that the algorithm's optimizing for student rating, but actually it should also combine some measure of learning? Well, how do we guide the algorithm to optimize for the right thing based on expert knowledge? And I think, interpretable machine learning, many of you have heard of this idea before, right? Interactive machine learning, these are broad terms. I think they're especially interesting in the context of like exploration and exploitation, in the context of experimentation, because that's where real intelligence can really be helpful in determining what actions to take. And so that's actually motivating a current line of research. So I've developed this tool for involving instructors in designing experiments. So in Access, students generated explanations and we tested them out. But what if we can actually have instructors try and play a bigger role? And what if they're not just generating explanations, but really any kind of message, motivational messages, learning tips? And so this was actually deployed with several instructors at Harvard, where I was before, but we're actually integrating it into Ideally now. So if you're interested, you could actually play a role in thinking, well, how do we actually bring HCI and machine learning into our courses on campus? How can we actually help NUS students learn by building these intelligence systems? And so the kind of key idea here is that we're thinking about how to get teachers to design these different conditions and then actually apply these dynamic analysis so we can lead to enhancing. So just to give you an idea, teachers plug this into their class, and then they actually might have a question, their different answers, and they actually edit the feedback messages. So should they just give an answer? Should they give a hint? Should they give a full solution? So these are kind of actions that teachers can play around with. And to give one example of what this looked like, one teacher actually wrote quantitative explanations versus analogical ones that help students understand concepts in terms of everyday experience. And so what happened after a while is that the policy was constantly updating. So the teacher was able to look at this and say, okay, the mean student rating was 7.2 versus 7.5. They were 46 versus 56. That's standard deviation. And so they actually had a sense of, okay, I can see why the problem is being updated. So they can actually look at this data and understand how this algorithm is actually improving experience for students in their classroom. What's interesting, though, is that actually you can see that this teacher actually predicted that we asked them to rate the likelihood that each condition will be better. They said 7 out of 10 for the quantitative and 5 out of 10 for the analogical. So this is why these algorithms are really important. In fact, if we had used this as a prior, because the teacher said 1 was 7, 1 was 5, maybe we could have said, well, you think it's better. Let's give 75% of students the one you think is better and 25% the one you think is worse. Well, what would be good about that is that you get the benefits of Bayesian inference. If their prior was correct, we quickly get to the right answer. But if they're wrong, we still actually can use this data to overwhelm their priors. So you can see how it's really important you have to kind of use people's judgment, but actually bring in these more empirical methods, because often we're wrong. With the predictions and what we think is going to help in teaching isn't actually correct. So this is kind of a big line of research, and it's kind of what I'm pushing on now in the next year or a couple of years. But let me give you another example that I think shows kind of the richness of this situation. So this is in thinking about how we use experiments to discover how to personalize. The context here was sending emails to people in an online course, a MOOC, or massive open online course at Harvard, where the person who came to me said, Joseph, I just want to figure out how do I get people to respond to this survey about why they're not in the course anymore. So they first designed this brief message. Please take the survey. And another condition we designed was one that mentioned absence. It's been a while since you logged in, so we want to hear about your experience. So you want to test which of these messages, brief versus mention absence, will actually increase response rate. So what do you guys predict? Brief, mention absence. What do you make of that? Actually, there's no significant difference between response rates. So at this point, well, you just pack up and go home, right? Waste of time. Actually, if you break this data up by whether people were low or high activity, what do you see? People who were low activity, meaning they hadn't logged in, they logged in 0 or 1 days in the last month, they actually were more likely to respond to the brief message, perhaps because they were more likely to just read this at all. People who are high activity, meaning that they logged in 2 or more days, were more likely to respond to the mentioned absence, perhaps because they've been active in the past and now wanted to explain why they weren't participating now. So what you can see is that by breaking data up in this way, we can actually optimize. So let's say that we use this data so that for all future people, if you were low activity, you got the brief message, and high activity, you got the mentioned absence, we'd actually have optimized, resulting in 40% more responses. So you can see now experimentation is actually a bridge to personalization. We can discover what's working empirically. And on top of that, by using machine learning, we can actually take any A/B experiment, which seems so simple, and turn it into an engine for personalization. It basically is a system that's intelligently figuring out what works for different people. This is, again, a simple example. So let me show you one that's a bit more complex. So actually, I just showed you 2 conditions. In fact, we ran wild. In that email, we experimented with the action space we were taking was there were 3 different subject lines. There were 3 different intro messages and 3 different response formats. So it's actually 3 by 3 by 3. So in all 27 different emails, but they've got this underlying low dimensional structure. 3 times 3 times 3. So you could analyze it just in terms of like, which of these was most effective. Also, we had a lot more context that I mentioned before. We had things like how active they were, but also how old they were, what country they're from, what activities they engaged in. So now you can see this is really getting towards a really interesting set of problems in terms of computationally. How could we actually use relatively sparse data to figure out how to personalize? In this setting, we did have thousands of people, but in general, I think an especially good area for future research is what are methods for machine learning that work well for small sample sizes? Small being hundreds, not thousands or millions. I mean, I wouldn't say this in public, but honestly, if you got 1 million data points, in a way, your problem's kind of a bit easier, right? But I'm really interested in how can you actually use just hundreds of observations to quickly get at what's working. This is especially important because even if you have 100,000 people doing a study, when you have 5 conditions, that's not bad. But as soon as you want to discover how to personalize, data gets sparse very quickly. Because if you want to figure out which actions work for subgroups of people, then every time you make a subgroup, you're splitting your data up. So I think this is especially interesting in terms of what methods can we use to very quickly figure out how to personalize with just hundreds of observations in each action, or sometimes even 50 or 100. So this is a good example with emails, but this is just an illustration. If you kind of say to me, well, here's something I'm interested in health behavior. Here's something I'm interested in sort of motivating students. I've worked with a lot of different platforms and different data sets where we can actually think of how to deploy those systems in the real world. So to be concrete, let's say you want to one thing I've started looking at is how do we actually get students to manage their stress? So you guys are grad students, you know a lot about stress, right? Every day you're feeling it. One thing we actually submitted a paper on to Kai yesterday was how asking people questions, like what's bothering you now? Why do you think it's an issue? Kind of walking them through this process of looking at their emotions can actually have a big effect on whether they get depression or not. And so one thing you can imagine is with NUS students, you could imagine an app that basically tests out different questions to help them reflect on their mood. And then we're trying to optimize whether they report that their actual mood is increasing, but we can actually use a lot of different contextual data. So I work with this group called AllSet, so Institute for Applying Learning Sciences and Educational Technology, and they actually have combined this data lake. So for students across campus, they're actually putting together data about what people do in IVLE, which courses they're taking, whether they're in discussion forums, how much they're participating, what their sort of entry scores were coming in, what majors they are in, and even long-term outcomes, like what are their grades like in future years, or 2 years from now, what do they report is actually their income. So you can kind of see this kind of data set could be integrated with systems like this, where when you send people emails or when you send them an app that helps them reflect, we can actually see, well, which actions are working for different people. We've got this rich set of data about those people, about what they've done before, what activities they've engaged in, and we can also even ask them to provide more. So we actually have a very rich data set with students on campus to start thinking about how we discover how to personalize. Also, there are interesting computational questions. Normally, when you have a data set that's been collected already, you already know what you're optimizing for. It's been decided. But if you want to deploy the system in the real world, often you will find, and I found, you start optimizing for one thing, like people's ratings of what's helpful, and you realize that's actually not the best thing to optimize for. We should have optimized for whether they actually came to class more, or whether they participated more in a course, because that's actually what we're trying to maximize. So you've got these really interesting questions about how do we do exploration exploitation when we're actually constantly trying to hit a moving target, where we may not know in advance what the true reward function is. Any questions about that? Was the kind of key idea here clear? Yeah.
And actually, that was the first thing that came to my mind on the first one that you mentioned. Like, how do you measure how the empirical measurement affects your results?
Yeah, so I think I'm interpreting the question as how do we figure out what to optimize for? Yeah. How do we actually measure good outcomes? And so basically the broad answer is this is where I kind of rely on human computation from behavioral scientists. So any problem you tell me about, like stress, I can tell you, I know of 5 to 10 people who work on that and 40 papers that basically are all about how do we measure stress. So they've gone out and validated in the field. When it comes to learning, that's kind of especially my area of specialization. 20% of my time in doing experiment goes in figuring out what questions should we ask people. Because sometimes small changes make a big difference in whether you really get or whether they understood something. So that's where I draw on a lot of psychological theory. And sometimes you have to test out multiple measures and actually do analysis of which of them correlate with others. Which short-term questions about ratings of explanations actually predict long-term learning. So the thing I showed you probably seemed intuitive. We tried 3 other things and they weren't good. Because sometimes if you ask people, did you learn or not, their response is not informative at all. So really it's in using psychology research that I often decide how to measure outcomes.
So how many subjects were part of the measurement?
So just the measurement part, I'm estimating, but I would say in sort of like previous pilot studies, maybe a couple hundreds. But then of course, I don't just rely on my studies, I also read a lot of literature. So when you read a scientific paper in psychology, it's kind of based on, 500 papers that came before it. So I guess my idea would be, if you just go and do it out randomly, very low chance you're gonna collect the right thing. But if you're actually basing on some literature that's come before, then you know that 400 other people before you went and did the wrong thing. Now they're telling you how to do the right one. Yeah, and so kind of the thing here is now, there are a lot of interesting questions like, how do you optimize reward as a function of these different actions, as well as also context? So I'm especially interested in this question of, how do we think about how to factorize action spaces? Because if you think of this as 27 separate actions, that's not super efficient. Your data gets sparse quickly. And maybe that's a bad assumption. Maybe you should actually think about whether you can analyze these somewhat independently. Or maybe you can analyze them semi-independently. Like you can assume they're independent, but you have to include some terms for whether this factor interacts with this one. So I think those are really interesting questions that other people can, like Brian, probably have ideas of how interesting they are from like a NIPS ICML perspective, but I know that they're definitely things that are being faced every day when we work with instructors. Just give an intuition of how this personalization works, right? You could imagine thinking, well, for different age groups, let's actually just assign people equally probability, but then, what percentage of people respond to the emails? Like 3.8% of 18-year-olds respond to A, 1.6 to B. And so the kinds of things you might think of doing, this is just an illustration, right? Where let's say we go from 33% for this group to 48%. Well, where did that number come from? Well, the intuition is that you kind of want something that's basically saying, well, the probability of assigning someone to a condition should be based on how sure you are it's the best for them. But also, that's basically what Thompson sampling is about. But also, maybe it should incorporate how much you're hurting them by not putting them in that condition. So you can basically think of estimating, well, what's your response rate for that condition relative to the others? So 3.8% divided by 3.8 plus 1.6 plus 2.3. And so this is something I'm interested in pursuing as a bit of a tweak on Thompson sampling, where for Thompson sampling, if 2 things were, let's say the response rate here was 3.8 versus 3.5, eventually Thompson sampling would give everyone. But you have to wonder, is that actually an optimal strategy? If they're not that different in quality, maybe you should actually keep experimenting, because that would actually allow you the chance to discover, well, actually, on average, they look the same, but for this subgroup of people, condition 1 is better. In terms of thinking about the future, I think the key idea here for me is bridging designers, social behavioral scientists, and machine learning work. I see experiments as a way to bridge practical design, like instructors or people who make apps, with psychologists who are actually good at measuring outcomes and want to figure out how people learn, with actually statistics and machine learning. And so, as I mentioned, I'm really interested in interpretable and interactive interfaces to ML, especially ML for exploration versus exploitation trade-offs. So for example, instead of being a black box, is it true that these probability matching algorithms like Thompson sampling are really easy to understand? Are they better than things like upper confidence bound or deterministic algorithms? And how can we actually help people to understand how the algorithms using data to update policies? With respect to interactive ML, one thing I didn't talk much about was how much should we influence the exploration versus exploitation trade-off? Is there an advantage to actually bringing designers into the loop where a teacher can say, I really want to be sure this is the best thing for everyone. So they actually are going to want to explore a lot. Versus they're very sensitive. I don't want any students complaining, so I want you to exploit as soon as possible. This kind of question, exploration versus exploitation trade-offs, are especially important when it gets to personalization. The challenge is that once you start thinking about personalization, you don't want to optimize too soon. Because as we saw with that email study, two things that look the same, or even if one looks better than the other, could actually be worse for a subgroup of people. So once you bring personalization into the picture, figuring out what actions to take really becomes an incredibly tough computational problem. That's where we might especially need human beings to come in and help guide it. So for example, could we actually encode designers or scientists' prior knowledge about which actions are likely to work for different subgroups of people? So this is something where I'm not sure I would, you actually need some constraint, because you want to know which ones work for people who are low or high knowledge or low or high motivation. The data gets sparse very quickly. So it'd be helpful to actually have a teacher or a scientist try and give you some constraints. But you want these to be soft constraints. You don't want them to just say, okay, give all low knowledge people the high probability explanation. We actually want something like listing priors from them that can actually guide exploration. And so just Brian, just throwing out an idea, I think this is where I especially start to think about Bayesian optimization, because you can imagine like in the covariance matrix trying to capture, okay, these actions work well for certain subgroups, but I'm not so sure. These actions work well for others, and I'm pretty sure. And in general, one thing I've been doing is rolling out this software specification, this Adapcomp Mooklet framework. And what it basically is it guarantees that any A/B test anywhere can be turned into one of these reinforcement learning agents. So it provides APIs where people can experiment as normal, but then you can actually write algorithms that will make API calls to actually get data. And so you can actually see, well, at this point in time, here's how many people have responded to this problem. Here's our estimate of whether it's a good action. Also, the kind of key thing here is that this allows these experiments to make API calls out to your algorithms. So kind of think about that a bit. If you think of a learner interface like a problem and there's a resource, if you implement this in Mooklet, Mooklet is a software requirement specification that basically guarantees that you can plug in things like reinforcement learning. So if anyone here is actually in a software engineering group or knows people interested, I'd be really interested in understanding, is there a software engineering paper to write about this kind of topic? Is there something that could be of interest here that's kind of a bit separate from either the teacher-centered part or the machine learning part? The kind of key idea here is that when someone is being assigned a resource like an explanation, it's actually done through an API call that gets sent out. And so what that means is that you can actually then substitute in different policies. You can start off with equal probability 50-50, but you can change it over time by actually making a call to banded algorithm or reinforcement learning or Bayesian optimization. Also, you can actually move from experimenting to personalizing. On the other side now, there's a version set, so the set of actions. And abstracting this out is what allows us to actually crowdsource from students and allow teachers to write these. And then finally, there's the learner data store. Because again, a key problem is most systems will not give an algorithm access to the data you want. So this is again a way of abstracting out what data is private enough, anonymous enough that an algorithm can actually pull in real time to see, here's how one explanation worked for people with low knowledge. Here's how a new person who's come in, here's what we know about them, so you can decide what action to give them. So basically, this Mooklet idea is like an abstraction for reinforcement learning. So that's the kind of key takeaway here, is thinking of how you use experiments to bring practical design together with psychology and actually machine learning. Another idea is to push this to other applications. Everything I presented here isn't necessarily restricted to education. So for example, I've also worked on how we can actually help people change health behaviors, like reducing depression. And in fact, if you think of a problem like smoking, one of the best treatments for this could actually be providing people with support that help them manage addiction. So think of, for example, of an app that would actually ask people reflection questions like, what's the best way for you to avoid smoking today? Or how will smoking negatively impact your family? And then people could also get motivational messages, right? Reminding them that the reason you're doing this action is because of this plan you made last time. If you don't smoke today, then you're going to be able to exercise more tomorrow. And one, I think, really interesting idea here with respect to personalization is if I give you an app like this, whether it's for quitting smoking or helping you plan your day or making you eat healthier, you could personalize it by actually saying, well, here's a question I want you to ask me tomorrow morning. Am I going to have Cocoa Pebbles for breakfast or Char Siu Bao? Here's a message I want you to send me when I follow through. So you can actually personalize this kind of app to you. But also, we're crowdsourcing from you because a message that works for you personally, we can actually test out on someone else. So you can imagine, really, we can take any app, implement these components as these MOOClets, and actually find ways to crowdsource ideas from people and then use machine learning to figure out what's working. So I kind of see this as a much more general framework. And I think there's a growing research understanding that a lot of the health problems, they might seem biological in nature, but actually the solutions are more likely to be psychological and computational by building systems like this. So to conclude, I started with this vision. How do we build perpetually improving systems? Take something as boring as a math problem or a website and make this an intelligent agent. And my approach is to rethink experimentation, A/B testing, so it's collaborative, dynamic, and personalized. I gave one example of this system, adaptive explanation improvement system, that crowdsourced explanations from learners by using banded algorithms to discover what's highly rated, identified explanations that help learning just as much as explanations from a real instructor. I also showed how this can actually lead to systems that actually bring teachers into the loop, where teachers can actually be the ones generating the actions, or in future work, trying to encode their priors, interact with the algorithm to guide it in what it's discovering. I gave one example of how experiments can lead to discovering how to personalize in the context of sending motivational emails that worked for people at different levels of activity. But really, that was an illustration of just the very beginning. How with rich data about people's contexts, we can actually think about designing algorithms that can figure out in real time how to personalize from experiments. I talked about kind of in the future, how we can use this as a bridge between design and psychology and machine learning, and especially how we can apply this in a wide range of contexts, from the problems you use in Ivy to apps you might use to eat healthier, to actually many other settings I'm sure all of you can think about. So thanks a lot. Questions?
What other kind of human computation is possible, apart from explanations?
Yeah. So I think one thing I'm especially interested in now is helping people come up with questions that they want to be asked. So we're looking at actually, all of you have to plan every week, right? We all have to plan, but we don't always plan that well. So let's say that you're getting a web app that would ask you questions like, what do you want to get done today? Is that the most useful question for you? Well, actually, there's a lot of research that planning is something that really has to be personalized. Some people hear, what do you want to get done today? And they're great. They know what to do. Other people need more support, like, what's the main obstacle you have to overcome? Or what are the things most likely to sidetrack you today? So I think actually using human computation to have people generate questions could be especially powerful, because people have a lot of knowledge about what questions work for them. And so in a way, it's not just having them generate, here's some information that could help. It's actually saying, what do you want the environment to ask you? What do you want someone to sort of help talk you through? So I think that's one direction I think could be especially powerful. It's also nice because if you think about any app, right, it can always have questions that ask you, that ask you to reflect. And so question is actually something that's almost like a gateway into cognition. When you're looking through Facebook, right, when you're on your website, having questions that kind of guide your thinking could be really powerful.
In the personalization case, where we personalize, using the age of the student.
Yes.
Right. So what if we have many features or contexts, and due to which the subgroups are not disjoint?
Yeah.
They overlap. What do we do with that?
Yeah. No. So I think that's a great point. So just say a bit more. When you say that they're overlapping, you mean, for example?
So say they fall in both categories in one feature, but
so like the 80-22 and but also, low activity. And also, don't like posting a discussion forum. Yeah. So I think this is where you have to actually make, you could make a simple independence assumption that all these features are totally independent. And that actually, you could probably get a long way on that. But that's something that has to be tested. Could you just assume that you can say, here's the message that works for people who are young versus old, and separately, here's the message that works for people who are active versus not. And just kind of ignore the fact that there's any relationship. That's one possibility, but I think that has to be tested. You could also think about trying to model interactions, like statistical interactions, like people who are young and also not active may be especially receptive to this kind of motivation message. But I think that's a good question for kind of future work. And ideally, I can tell you how that kind of question is answered in behavioral sciences. You sit there with a data set and you go over it tons of time and you try different things. If we could think of ways to actually do that in a semi-automatic way, that would be very useful. When should we just assume everything's independent versus when can we do some kind of simple statistical tests?
So for the explanations that you have generated earlier, it seems like there is no finite number to begin with. But on the other hand, usually when we look at the use of probability, we need to fix the number of say possible explanations in the first place, right? So
no, that's a great point. So that's why I basically every time a new explanation was added, you essentially have to recompute the probability distribution. So that's what we do. But actually, with Thompson sampling, that's actually incredibly efficient. Because just for you guys, the way Thompson sampling works is you have a set of explanations, right? And you want to say, well, what's the probability of selecting each? You don't write down that probability distribution explicitly. You don't have to write it down and compute it. I just did that to show you. What you do is you actually sample from each distribution. So you sample from the distribution of explanation 1, and you get like a 0.9. You sample from explanation 2 and get a 0.7. And what Thompson sampling says is just choose the highest one. And if you do that, then on average, you're choosing, if you just choose the highest sample, then on average, you're sampling with the probability that that's the best explanation. And so that's actually really good because you can just keep adding new actions. It's also actually why a lot of these design choices matter. So what we did at first, which did not work well, was we actually had uniform priors. So we actually said, well, every new explanation, let's just imagine there was one success, one failure. Actually, that didn't work well because it meant that new explanations would not get tried out quickly. Because if you have a uniform, it's essentially saying, well, I think the rating is about a 5. But what that meant is that if any of the explanations looked like they were a 6 or 7, the new one would not get tested out. So what we did by saying that every new explanation, let's act as if it has a 9 or 10, means we think it's really good. It's a 9.5. But we're not very confident in that. So it means that every new action we test out quickly, but as soon as we get negative data, we stop presenting it. Thank you. Thanks so much. And feel free to come up and chat with me. Okay, thanks. Yeah.